Hi everyone, this is our week 3 video on unit 3C, petroleum as a builder molecule, so something that can build other things. We're going to look at a bunch of things today. This is kind of a packed presentation. We're going to look at the difference between a monomer and a polymer and how the molecular structure affects physical properties of a polymer. We're going to compare saturated and unsaturated hydrocarbons in terms of structure and properties. We're going to look at functional groups like alcohols, carboxylic acids, and esters. We're going to identify and describe 2 major classes of ring compounds. And we're going to look at the roles of addition and condensation reactions take in polymerization, which is the forming of polymers. So there's quite a bit today, and we're going to cover it all. So first, polymers and petrochemicals. A polymer is just a large molecule. It's typically composed of 500 to 20,000 or more repeating units of a simpler molecule. And those simpler molecules are called monomers. So if you have a monomer, you have one. If you have a polymer, you have many. Mono means one and poly means many. What would a dimer be? How about a trimer? If you said a dimer would be 2 monomer links, you are correct. If you said trimer or 3 monomer links, you'd be correct. Petrochemicals are just compounds that were produced from oil or natural gas. This could be detergents, pesticides, lots of pharmaceuticals, and cosmetics. Most petrochemicals will serve as raw materials or starting materials for other man-made substances. And this includes synthetic polymers. So not polymers that are found in nature, but ones that we've created. This includes paint components, fabrics, rubber, insulating materials, foams, adhesives, molding, and structural materials. A polymer structure can vary significantly. So the structure is largely the reason for the properties. First, we have to understand what they are, and polymers are created by an addition reaction. And so this picture here is the addition reaction. You have this ethene molecule, and it's going to react with a water molecule, and it's going to create one molecule. Notice they've added together. We've created this longer piece. This double bond has become a single bond, and this hydrogen has bonded to one side of the compound, and the OH has bonded to the other side of the compound. So we've added these 2 things together, and that's called an addition reaction. So a little background on that is that a single covalent bond, you would see C-C, so like this one here. That's demonstrating 1 pair of valence electron, or 1 pair of shared electrons. They are valence electrons. So 1 pair of electrons would mean that there's 2 shared electrons. So the single refers to 1 pair. When you see 2 lines like this, it's a double covalent bond. Each line still represents a pair, so the double line represents 2 pairs of electrons. So a double bond has 4 shared electrons. How many lines would you see for a triple bond? If you said 3, you are correct. Now, these addition reactions will create long chains of repeated units. So you could have this single unit that's a vinyl chloride, and when you add it together, you're going to get that same unit repeated over and over again. And that's now poly, or many, vinyl chloride. You might recognize PVC. Lots of times we've heard of PVC piping. It's used for many other things. Acrylonitrile is this one here. That's the monomer, and when we use an addition reaction, we connect many of them to create polyacrylonitrile, or PAN. In this last one here, I have to wait for the menu to disappear so you can see it. That last one there is styrene, and you've probably heard of polystyrene. So this example here, right, is all the styrene monomers connected to create many styrenes, or polystyrenes. And each of these have a different structure. So whether it has the chlorine coming off of it, or a CN, which is a cyanide ion, or this circle here, this circle with the hexagon around it, which is a benzene ring. And we're going to talk about what that means as well. So an unmodified polymer, one that's not changed at all, would be long and string-like, and it can coil loosely. You can imagine that it looks a lot like cooked spaghetti all coiled together. So this would be this is what we're going to use to represent a string-like monomer, a string-like unmodified polymer. Now, temperature can affect the flexibility and ductility of these. So ductility is just the ability to draw something out into that strand. We've talked about it in terms of metals being ductile to draw them into wires. That provides our copper wiring in our houses. Polymers can be ductile too, and now we're going to call it a thin strand instead. So when polymers are cool, they can be very rigid, and when they're warm, they can be very flexible. And these polymers that can change with temperature are referred to as thermoplastics, like soda bottles, milk bottles, and plastic bags. You can also use an internal lubricant to increase flexibility. An example is PVC, that polyvinyl chloride. It's very rigid, and so that makes it good for pipes and siding. But if you add an internal lubricant, now you can use it for a raincoat or an inflatable pool toy. Much different properties with that change in the structure. There's also something called a branched polymer. A branched polymer is when there's side chains, and they affect the ability for the chains to slide past each other. This also changes those intermolecular forces, which we talked about last time as something that changes the boiling point. And this picture here is what we're going to use to represent branched polymers. You can see the long string-like chain with side chains, or those branches coming off of it. And last, there's cross-linking. And cross-linking will make something more rigid. So we say it increases its rigidity. And soda bottles and their cap are two different polymers. The cap has cross-links, it's much more rigid, and the soda bottle does not. And this is our picture to show cross-linking. So it looks a lot like a ladder. Saturation. So a saturated hydrocarbon is going to be one that has all of the carbons have as many single covalent bonds as possible coming off of it. So these alkanes here, this example, has all single bonds, and there's 1, 2, 3, 4 bonds coming off of the carbon. That's considered a saturated hydrocarbon. An unsaturated hydrocarbon is when not all of the carbons have their full capacity bonded. So they might not be bonded to 4 other atoms. So in this case here, there's 1, 2, 3 bonds between that carbon and 3 other atoms. There's a single bond, and a double bond. So that only counts for 3 connections. This is an unsaturated hydrocarbon. An addition reaction could now make it saturated. Alkynes have triple bonds, and you would notice that this carbon only is bonded to 1, 2 other things, so it's definitely unsaturated. When we talk about a substituted alkene, we're talking about when there's something besides hydrogen and carbon. So it might be oxygen or nitrogen or chlorine or sulfur that's also bonded to the hydrocarbon. So to get a better idea, the builder molecules, an alkane is anything with a single bond. And we talked about those in the last chapter, or one of the last units. We refer to those as methane, ethane, propane, butane, pentane, hexane, heptane, and so forth. And those are all alkanes. Notice that their ending all ends with ane. Now, you might have the same length carbon chain, but with a double bond somewhere in there. Now, it's going to become an alkene. If there's at least one double bond, we now refer to it with an ENE ending. So this ethane now became ethene. If we have a triple bond in the compound, it becomes an alkyne. So now the alkane, alkene, alkyne, and that's if there's at least one triple bond. A cycloalkane is when you have a ring shape. So this would be a ring shape, but this isn't a cycloalkane because the other stipulation is that there's all single bonds. This is an aromatic or an arene. and it's drawn with alternating single and double bonds in a ring shape. So you notice there's a double, and then a single, and then a double, and then a single, and a double, and a single, and it keeps going. That's that alternating. These are known for having really nice scents or really bad scents, but they are aromatic. They have strong scents. These builder molecules can also have, can also include things with certain functional groups coming off of them. Now, a functional group is an atom or a group of atoms that imparts characteristic properties to organic compounds. So we use an R to show the rest of the molecule, and everything else is unique to that type of functional group. So in alcohol, we hear a lot about alcohol, right? Rubbing alcohol is isopropyl alcohol. And we hear about a lot of different alcohols out there. They all end with an OL ending, so isopropanol, you hear that OL at the end, and they all have an OH group attached to the rest of the molecule. So if there's an OH, you know that it could possibly be an alcohol. It's not a guarantee because carboxylic acids also have an OH group, but they have that OH group is bonded to a carbon that's also always double bonded to an oxygen. So you're going to see these three things connected at the end of the rest of the molecule. And that's a functional group that's a carboxylic acid. And the last one, an ester. An ester is also has nice smells to it. It has a functional group, it has the rest of the molecule connected to a carbon, which has a double bond to an oxygen and a single bond to an oxygen. And then another rest of the molecule here. Now notice that this has this little apostrophe next to it. These two R's that are the rest of the molecule don't have to be identical, but there will be these three bits, that oxygen double bonded to a carbon and bonded to an oxygen in the middle of a compound. That's going to be an ester. So why are these important? Well, carboxylic acids can be found in ants and vinegar. Alcohols are an antifreeze, windshield washing fluid, rubbing alcohol, cough medicine, hairspray, and aftershave lotion. It's probably the most popular one, the one you're most familiar with. And esters, like I said, they have scent, they have smells to them. So you're going to find those in flowers and in bananas, and some mints, and lots of other fun things. Now, we talked about addition reaction before. I'm also going to tell you the opposite, which is a condensation reaction. So remember addition reactions when water was added as the polymer chain grows? Well, a condensation reaction is just the opposite. The water is lost or removed as the polymer chain gets longer. Both of these are forms of polymerization, so they're both going to grow the polymer or make the chain of polymers get longer. So it creates a polymer. But in the example of addition, we add water and the polymer chain grows. In the example of condensation, we're actually going to react these two things together, create a longer chain, and the water is a product. It gets removed. So let's review. Polymers. Monomer means one link in the chain, where polymer is many links, or it's a chain of links. Saturated, when we're talking about hydrocarbons, are when the carbons are fully bonded. They bond with 4 other atoms. And unsaturated is when the carbons form bonds with less than 4 other atoms. So it could be 3 other atoms or it could be 2 other atoms. Polymerization is when we grow the polymer or the chain of the polymer gets longer. This can happen through an addition reaction where water is added or through a condensation reaction where the water is removed. And we talked about functional groups. Different examples were alcohols, carboxylic acids, and esters. These affect the properties, and therefore they affect the purpose. It changes, those properties change how we use the polymer. And then we had ring compounds. We had a cycloalkane, which had all single bonds, so that's considered saturated. And we had aromatics, which were an alternating double and single bonds, and so it's unsaturated. As always, please send questions to my email or through comments on Google Classroom. Thank you.